Here I am again. I was going to put this off until after the midterm break, but I'd like to get this in so maybe we can have a few exercises in our midterm exam. Uh, I want to do some talking about double act, some more talking about double acting cylinders. I think I've explained this once, maybe several times. There's, there are good explanations and illustrations and problems in the textbook. Uh, I just wanted to take the time to go over it with you and look at a little hypothetical situation I put together down here and talk to you about the difference in a single acting and a double acting cylinder when it comes to calculating Pascal's variables. Force equals pressure uh, times the area, especially the area, will make a difference. In a double acting cylinder, first of all, I put some subscripts in here as the book did, but you're going to have two areas to consider in this. In the single acting, we had hydraulic fluid under pressure entering here, entering, had hydraulic fluid under pressure entering here and applying pressure in this direction. And remember, so I talked about a double action valve down here. So that would be needing, and I think there's more to this is a double action, but it's something to let fluid do two or three things, and I'll talk about that. That's very poor schematic. But it allows fluid to come, well, I got my line over here, but to come through this valve into, the valve would be over here, into this port. It fills this void in here with hydraulic fluid until it meets resistance again, you know, the which is the face of the cylinder. Now, as it begins to move the rod in an extended manner, extension means to go, you know, the rod goes out. Retraction, the rod goes in. So as it begins to move this rod in this direction, if there is leftover fluid in here, it's going to come out and have free flow all the way back to the reservoir. Most likely. Now, there are exceptions to this when you have two cylinders operating like the swing on a boom. You're going to have them in a series or parallel, I forget, but like one's pushing the other while the other one's pulling. But in this case, all we want to do is go right and left. And we talked about putting a bucket on the end of this clevis pin area here. And, you know, I think in our illustration on the last video, when we extended by putting pressure here, we had a backhoe bucket drawn here, and I decided that would be the curl. Now, when you move that control, it changes this valve. Then it allows pressure to come in to here in this manner. Got too many lines, but we're going to deal with it. It allows hydraulic fluid to come here, and again over here at the same time that valve has a spool in it that opens different pathways for the fluid. It allows this fluid to go without, well, this natural resistance, but just move freely back into the reservoir or And the same thing over here. This fluid comes back out and goes into a reservoir. The same one, I'm sure. It's just schematically it's drawn like this, and schematically it doesn't have waves, I don't think. So, but anyway, back to what I was saying. There are two considerations for area. You have an area here that's flat. It looks like this. It's just flat. I don't have room to put it up there. But I do have room to put it here. You have, this is what you're looking at when you're looking at this. This is what you see. Now, this area, this has a dimension, as you see. Here I gave it a dimension of 4 inches for the bore and the cylinder, if you recall, are the same in diameter. Over here, remember the word annular we talked about? That's when you have an area that's round, and then it could be a hole. In this case, it's the end of the rod. Let's see if I can. That's the piston. See, it's just sticking out from the piston, and down here is where the little eyelet is to go. So this has an area, right here when I'm looking at this, and it takes away from this area here, which is really this area that we first started talking about. So you have two calculations. You have an area calculation to do on what's known as the rod end, the end that the rod is moving, and some people call it the cap end or the blind end, and that's the end where there is no rod in this case. Now, all exceptions, there are some that have rods there, but in this case, and what we're going to talk about, you'll be able to take advantage pressure-wise of all the area of this circle, this 4-inch circle. Over here, you're going to have to find the area of that surface, and you're going to have to find the area of this effective surface, it's called. In other words, that's all the surface that's not taken up by the 2-inch rod end, which is a circle. So we need to take, and this side and this side are the same in diameter, but as far as area goes, this rod, 2 inches diameter, takes up a certain amount of area. So you have to calculate this area, right? And then you have to calculate that area. That means you have two areas to deal with. So it's going to be, when we get through with this, it's going to be this area, which is the same as this except for rod. This side, the annular side, the annular is going to be this same area minus the area of the 2-inch rod, which has its own area. See, it's 2 inches, so it'll have an area. Now, in a double-acting cylinder, force capability is different on extension versus retraction. Extension is where you have the access to the whole surface of the piston. On retraction, you have access pressure-wise in this direction on the whole surface 4-inch diameter circle less the 2-inch diameter circle. So when you put 125 pounds in here, or let's say here, maybe you're going to have 2,000 pounds force. When you put 125 in here, you will have you will have less areas, so you're going to have less than 2,000 pounds, right? Right, because you're going to subtract the rod end area. So on retraction, the area subjected to hydraulic pressure is less than on extension. Typo there. On extension, because the area taken up by the rod is not used to move the load. On extension, that's going that way, pressure going that way, coming in this way. On extension, the effective area is the entire face of the piston. On retraction, the effective area is the piston area minus the rod area. You don't get access like you do over here to as much surface area. So you're going to have different forces as you come with the same PSI coming this way. You will not have the same force as you will. You will not have as much force as you would with the same pressure coming this way. So the way to go about that simply is to calculate the effective area on extension. That would be that area. Consider the entire face of the piston. So in this case, you would be having a piston with a diameter of 4-inch. In this case, you'd have a piston. You would have a circle with the area. With the diameter of 2-inch. Calculate the effective area here on extension, and consider the entire face. Use the formula A, same one, equals pi times the diameter squared, and that little subscript is for the piston, divided by 4. It's what we did in the last video. To calculate the extension force, use the formula of force for extension equals pressure times area of the piston. That would be that area. The rod area is did you get the force? It's pressure times the area. Pressure times the area. For extension, that means you're going this way. The next step is to calculate the effective area on retraction. And when I say effective, that means you don't have this hole. You have a hole. You have this annular area. Calculate the effective area on retraction. The piston area, you would calculate the area or use this area, and then calculate the area on the rod and subtract the area on the rod from the area you calculated up here that I noted as the piston area. Oh, the effective area. I'm going back and forth a little bit here. To calculate the effective area, that means what's left. What's left this way is everything. What's left this way is the annular area. To calculate the effective area on retraction, that would be piston area, what you got up here, minus rod area, what you'll get when you calculate the area for a 2-inch circle. I don't know why I changed that. Use just the formula, just the regular formula. Use just the regular formula. I think that's a typo. To calculate the effective area on retraction, the piston area minus the rod area. I'm not sure what I meant by that. But this is effective area would be here minus the rod end area, which would be this annular thing. I think I did one down here. Let's see if I can get this up a little bit more. I have a big desk, but it is all filled with stuff. Okay, we'll get that. Let's come this way a little bit with the Elmo. I think it's its name. All right, maybe that's good enough. So when we get into the calculating part of this, we're going to say we are given a pressure of 125 psi. Also, we up here we were given a diameter. We have a diameter that equals 4 inches for the extension, and we have a diameter that equals 2 inch for the retraction. So to get this retraction area, we'll subtract it from the extension area up here. So nothing is changing from the last video. In the double acting cylinder above, calculate the extension and retraction force. So we're going back to force up here, but we're not there yet. Right here is where we get into the force. And we didn't do a lot of that yesterday, if any. But force is its own formula. And remember this thing right here that tells you what to do with what you have. Put force right in this little gap or holes. Put pressure right here. And you put area right here. So once again, if I want to know the area, I take the force divided by the pressure. If I want to know the pressure, I take the force divided by the area. If I want to know the force, I multiply the pressure times the area again. That's force equals pressure times area. So this is just a simple area calculation, but let's kind of run through it right quick. So A is for extension. Now we're calculating this whole area here. So the thing's supposed to autofocus. There we go. The area for extension is the same formula we use. Pi times the diameter squared divided by 4. And what that equals is pi 3.1416 times the diameter squared, which was 4. That was our given right there. Diameter 4 inch, and it's also in the drawing. It's squared, and then that's divided by 4. So we're going to keep narrowing it down. We're going to get rid of this exponent, this little 2 here next. So we'll say that equals 3.1416 times 16. So 16 right there is where we got rid of this guy, right? We made this a real number. So 3.14 times 16 times 16 divided by 4 equals 12.566 square inches. Inches squared. Let me go scoot for the extension. And that's the first one. So that's going in that's the one for here. When you're going in and you're putting pressure and you're going to extend this rod out this way. Okay, so we got that. And I got it kind of isolated in a square. Hopefully not losing my place. So next we're going to take this one, and look what we're dealing with. We're dealing with the, you can't see him, but he's hiding right here. The 2-inch square right up there. We're going to use the 2-inch diameter circle. Can I get my self square here? Okay, so that calculation is going to be pi times the diameter squared divided by 4 equals 3.1416 times 2 squared divided by 4. And we want to get rid of the exponent. Remember PEMDAS, parentheses, we don't have any, so we go to exponents to get rid of. So 2 squared divided by 4, that's the same as 3.1416 times 4 divided by 4, which is 3.14 inches square for retraction. Okay, so we got this area for retraction. That's the area for a 2-inch circle we just did. There's the 2-inch that we used from the diameter that was up here, 2-inch. So what are we going to do? Let's do force for the extension right there. The formula for force is pressure times area. Okay, so here's the pressure, 125 psi times area, pressure times area. Here's the area, 12.566 square inches. And that equals 1,570.75 pounds per square inch. That's extension. So the force for retraction is the 2-inch. We got that 2-inch area up here. So, and we came up, there's the area right there. So here we got, wait, why have I got 9.46 square inches? Give me a minute. Let me see if I got a error. What did I do here? Let's calculate this area for the 2-inch, 3.14 times 4 divided by 4. 3.1416 times 4. And see, in this case, we have taken this 2 squared and changed it to 4. So 3.1416 times 4, and that equals that's a coincidence. That equals 12.566 divided by 4. That equals 12.566 divided by 4. And that equals 3.14 square inches. So take your force on retraction is the, why am I got this 9? Oh, for goodness sakes. I'm going nuts here. Look at here. But all I got to do is take this area. I don't know why I'm making this so complicated. I'm working in force now. So just take, I need an area here. So take the 12.566 and subtract the rod. My goodness. That's what you're going to get for retraction. That's no mistake. That's just me not knowing what me has done. So again, this is full extension. This is area for retraction. Area for extension minus area for retraction gives you the area for calculating force. Let's see if I'm right after all of that. So I'm going to take 12.566 and I'm going to subtract from that 3.14. That's not hard. It gives me 9.4. Well, I said 46, but I'm going to leave it there. It's really 426. That should not be, but I'm going to leave it there since it's calculated. So when you multiply 125 times 9.46, 125 psi, 125 times 9.46, you're going to get 1,182.5 pounds. So see, when that cylinder is retracting, when that cylinder is moving, when pressure is coming in at 125 and pushing this way, you're going to get a force of 1,182. When pressure is coming in on this side and you get the full surface area, you're going to get a force of 1,570.75 pounds per square inch. And this is also pounds per inches square per square inch. Okay, what I want you to do, we've gone through this. You can go back and revisit the tape. I think it's going to come out, the tape, the video. I think it's going to come out pretty clear, if I come out pretty clear, and I think you'll get it. But again, the standing offer is, if you see something like you can't figure out, and even if you say, I think you made a mistake here, can you verify that so I'll know if I'm right? You know, that's a legitimate phone call, is to call me out on making mistakes. We're dealing with math, and it can happen. So I'm going to leave you with that. There's a tailgate. I hope you make interesting for me. I gave you some places to start. There's the video at the beginning of Module 4, and I'll come up with a few questions for you before the end of the week so that we can have it'll probably just be some problem solving and things that we've done. I'm not going to stress you out. We are going to have in the 5th week, we will have, which will be the week when we get through the next week, we'll have a midterm exam over what we've covered. And just mostly, you know, we want to score good on it because it'll help our grade. I want to see where you are and, you know, what I could do better, what you could do better, and things like that. So if you get hung up, remember, give me a text, call me, email me, or use the Canvas inbox. You guys have a good week.